James Webb did not see Pluto for the first time. Spacecraft and ground telescopes had already observed it for many years. New Horizons had even flown past the dwarf planet and revealed mountains, glaciers, valleys, and a surface far more active than anyone expected. But Webb has now looked at Pluto in a completely different kind of light. It has studied the faint infrared glow coming from the Pluto and Charon system. The glow carries information hidden from ordinary cameras. It reveals heat, frozen chemicals, atmospheric haze, and changes taking place across a world that many people once thought was nothing more than a frozen rock at the edge of the solar system. What Webb found is not impossible. Because Pluto exists, it is surprising because Pluto is still changing. The title sounds dramatic because the truth is dramatic enough. James Webb saw Pluto in wavelengths that earlier missions could not study in the same way. It detected heat coming from the system and helped researchers examine the haze surrounding Pluto. It also studied Charon, Pluto's largest moon, and revealed chemical traces on its frozen surface. These discoveries do not prove that Pluto contains life. They do not show cities, oceans, volcanoes, or anything that breaks the laws of nature. But they do show a system that is more complex than the simple picture most people carry in their minds. Pluto is small, cold, and distant. Yet the physics operating there connects atmosphere, surface ice, radiation, sunlight, and the long passage of time. Pluto is located in the region beyond Neptune, in a vast area called the Kuiper Belt. This region contains countless pieces of ice and rock left over from the formation of the solar system. Pluto is one of the largest known bodies in that distant zone. Its orbit around the Sun takes about 248 Earth years. That means a season on Pluto can last for decades. A human being cannot watch a full Pluto year unfold. Even several generations of scientists would see only a small part of its seasonal cycle. This creates a challenge for researchers. They must compare observations taken at different times and use physical models to understand how Pluto changes as it travels around the Sun. The sunlight reaching Pluto is much weaker than the sunlight reaching Earth. The Sun is still visible from Pluto, but it would appear far smaller and less powerful in the sky. The energy arriving there is only a small fraction of what Earth receives. Still, weak sunlight can drive important changes when the surface is made of volatile ice. On Pluto, nitrogen, methane, and carbon monoxide can freeze onto the ground. When conditions become warmer, some of that material can turn into gas. When conditions become colder, the gas can freeze again. This cycle changes the pressure of Pluto's atmosphere and moves material across its surface over long periods. That process makes Pluto different from a completely inactive frozen object. It does not need liquid water or volcanic fire to change. Ice itself can move. Nitrogen can migrate from one region to another. Methane can gather on mountains and high terrain. Frost can appear in one area while disappearing somewhere else. The atmosphere can expand and contract as the surface warms and cools. These changes are slow, but slow does not mean insignificant. Over millions of years, small movements can reshape the appearance of an entire world. New Horizons gave scientists the first close look at the terrain. Webb is helping them understand the energy and chemistry behind that terrain. Webb was built to study infrared light. Infrared light is invisible to human eyes, but it is extremely useful to astronomers. Warm objects release infrared energy. Molecules also absorb and emit infrared light in specific patterns. Those patterns can act like fingerprints. When scientists separate the light from a distant object, they can search for those fingerprints. If a signal matches the laboratory signature of methane, carbon dioxide, water ice, or another compound, researchers can identify the substance. The telescope does not see a label attached to a molecule. It measures the way light interacts with that molecule and then compares the result with carefully tested models. The same basic method is used to study distant galaxies, newborn stars, planets around other suns, and worlds in our own solar system. Pluto may be much closer than a galaxy from the early universe, but it is still difficult to study because it is small and faint. Its distance makes the object appear tiny in the sky. Its surface reflects very little sunlight compared with larger planets. Charon sits nearby, and the light from the two bodies can overlap. Webb must track their motion and separate their combined signal. This turns the observation into a delicate measurement rather than a simple photograph. In 2022, researchers used Webb's mid-infrared instrument to observe the Pluto and Charon system. The observations covered several mid-infrared wavelengths, including bands around 15, 18, 21, and 25.5 micrometers. These wavelengths helped researchers study thermal emission from both bodies. Instead of seeing only reflected sunlight, Webb measured energy coming from the system itself. That information can reveal differences in surface temperature and thermal behavior. A visible image can show that one region is bright or dark. An infrared measurement can show whether that region absorbs energy, releases heat, or behaves differently from the surrounding terrain. The observations showed significant variation in the thermal emission from Pluto and Charon. This was important because it confirmed that the system does not behave like a single uniform sphere. Pluto and Charon have different surfaces, different compositions, and different relationships with sunlight. Pluto has a thin atmosphere that can move material around the planet. Charon has almost no atmosphere and a different geological history. Their temperatures are shaped by different processes. By studying them together, scientists can compare two neighboring worlds that formed in the same general region but evolved in different ways. Pluto's atmosphere is extremely thin compared with Earth's atmosphere. A human could not breathe it, and it would provide almost no pressure at the surface. But an atmosphere does not need to be thick to matter. Even a thin layer of gas can carry molecules, transport energy, and interact with surface material. Pluto's atmosphere contains nitrogen, methane, and carbon monoxide. Sunlight can break methane molecules apart and create smaller fragments. Those fragments can combine to form more complicated carbon-based molecules. Over time, these molecules can become part of the haze surrounding Pluto. The word haze may sound harmless, but Pluto's haze is one of the most important features in its climate system. The haze is made of tiny particles created by chemical reactions high in the atmosphere. Solar ultraviolet light helps drive those reactions. The resulting material can scatter sunlight and absorb energy. Some particles may slowly settle toward the surface, adding dark or reddish material to the frozen landscape. The haze also changes how heat moves through the atmosphere. It is not simply a color effect. It is a physical layer that can influence the temperature and behavior of the entire atmosphere. Researchers studying Webb's mid-infrared observations found evidence that Pluto's haze can have a cooling effect. Now, this may sound strange at first. A haze particle can absorb sunlight and become warmer, yet the haze can still cool the atmosphere around it. The reason is that the particle can release energy as infrared radiation. Some of that radiation escapes upward into space. In that way, the haze acts like a collection of tiny radiators. It absorbs energy, warms, and then sends energy outward. The result can be a lower temperature in parts of Pluto's atmosphere than scientists would calculate from sunlight alone. This does not mean Pluto is cooling rapidly or that its atmosphere will disappear tomorrow. The effect is part of a long and complicated balance. Sunlight enters the system. Ice absorbs or reflects some of that energy. Molecules respond to radiation. Haze particles absorb and emit infrared light. Gas moves between the surface and the atmosphere. Each part affects the others. A change in one area can influence the entire climate system. Pluto is a frozen world, but its atmosphere is still participating in a delicate exchange of energy. The haze also changes what distant telescopes see. When sunlight passes through the atmosphere, haze can scatter it and give Pluto a layered or colored appearance. When infrared energy moves through the haze, the particles can absorb some wavelengths and release others. By measuring those changes, Webb can learn about the structure of the haze. Scientists can compare different models with different particle sizes and chemical mixtures. The goal is to discover which model best explains the complete set of observations. No single image can provide that answer. The chemistry begins with methane, but it does not end there. Methane contains carbon and hydrogen. When ultraviolet light breaks it apart, the pieces can take part in new reactions. Some of the resulting compounds may contain more carbon atoms and more complex structures. These compounds can grow into larger particles. As the particles grow, they can absorb and scatter light in different ways. They can also behave differently in the atmosphere. The exact chemistry is still being studied, but the broad process is well grounded in the physics of radiation and carbon-based molecules. It is important not to confuse organic chemistry with biology. Organic molecules can form without life. They are found in meteorites, comets, planetary atmospheres, interstellar clouds, and many other places. On Pluto, organic haze particles are a product of sunlight and atmospheric chemistry. Their presence does not indicate plants, animals, microbes, or any other living system. It does show that Pluto is chemically active. It also shows that the outer solar system contains environments where carbon chemistry can become complex, even under extreme cold. New Horizons revealed that Pluto's surface is far from smooth. The spacecraft photographed a huge basin known as Sputnik Planitia. It saw mountains made mostly of water ice. It detected broad plains of nitrogen ice and possible glaciers flowing through low areas. Some of Pluto's terrain appears young on geological timescales. That does not mean the surface is warm. It means that solid materials can move and reshape the landscape when conditions are right. Nitrogen ice can behave like a slow glacier. It can fill basins and move around obstacles over long periods. Methane adds another layer to this surface system. Researchers have found methane across many parts of Pluto. It appears in different concentrations and may be linked to variations in color and terrain. Higher regions can collect methane frost. Low areas can hold more nitrogen ice. Sunlight changes the balance between these materials. The surface is therefore not just a frozen shell with one constant composition. It is a patchwork of different ices responding to elevation, sunlight, temperature, and atmospheric exchange. Webb's thermal observations give scientists a way to compare these different regions. A dark region may absorb more sunlight than a bright region. A rough surface may radiate heat differently from a smooth surface. A layer of frost may insulate material beneath it. A haze-covered region may interact with energy differently from a clear region. These effects can be small, but Webb can measure their combined infrared signal. The telescope helps researchers connect what they see in images with what the surface is doing physically. Charon makes the story even more interesting. It is Pluto's largest moon, and it is unusually large compared with Pluto itself. Pluto and Charon orbit a point between them rather than Charon simply circling a much larger planet. This shared center of mass is one reason scientists sometimes describe them as a double world. Both bodies are tidally locked, meaning the same side of each body generally faces the other. Their relationship is ancient and unusual. They likely formed in the outer solar system and have remained linked ever since. Charon's surface is different from Pluto's. It contains water ice, but it lacks Pluto's substantial volatile atmosphere. It does not show the same kind of global nitrogen and methane cycle. Instead, its surface records impacts, radiation, and the slow alteration of frozen material. New Horizons showed a varied landscape with canyons, craters, and regions of different color. Webb has now added chemical information that was difficult to obtain before. The moon is not simply a gray companion. Its surface contains a history written in molecules. In observations made during 2022 and 2023, researchers used Webb's near-infrared spectrograph to study Charon across wavelengths from about 1.0 to 5.2 micrometers. The observations covered different viewing geometries. This allowed scientists to examine more than one portion of the moon and compare the strength of chemical signatures. The wider wavelength range extended beyond what New Horizons' surface spectrometer could study. That mattered because some important compounds absorb light at wavelengths that earlier instruments could not measure as clearly. The observations detected carbon dioxide on Charon's northern hemisphere. They also detected hydrogen peroxide on the frozen surface. Neither result is evidence of life. Both are chemical clues. Carbon dioxide can become trapped in ice or be exposed by impacts and surface processes. Hydrogen peroxide can form when radiation acts on water ice and rearranges the molecules. Charon is constantly exposed to ultraviolet light and energetic particles from space. Over billions of years, those inputs can change the chemistry of the surface. Hydrogen peroxide is especially useful because it points to radiation processing. A molecule of water contains hydrogen and oxygen. When high-energy radiation strikes water ice, it can break molecules apart. The fragments may recombine in new ways. Under the right conditions, some of that chemistry can produce hydrogen peroxide. The signal on Charon indicates that the moon's surface has been altered by its space environment. The process may be slow, but the passage of billions of years gives it enough time to leave a measurable fingerprint. Carbon dioxide provides a different kind of clue. It may have been present in material left from the formation of the solar system. It may have been exposed or concentrated by impacts. It may also have been created or modified by radiation chemistry. Scientists compare the location and strength of the signal with the terrain seen by New Horizons. If the carbon dioxide is stronger in certain geological regions, that could reveal how the surface was changed. The chemical map is still developing, but Webb has supplied information that was not available before. The northern region of Charon is particularly important. It contains a reddish area that has attracted attention since the New Horizons flyby. The color may be linked to complex carbon-bearing material, created from methane or other compounds. Webb's detection of carbon dioxide and hydrogen peroxide gives researchers additional markers to compare with that region. The chemicals may not explain the entire color, but they can help separate different processes. Some compounds may come from ancient material. Others may be produced later by radiation. The final appearance may reflect both histories. Charon also raises questions about material moving through the Pluto system. Pluto has an atmosphere, and some molecules can escape the dwarf planet's weak gravity. A small amount of material may travel outward and reach Charon. Over time, that could create surface deposits. The process would be slow and difficult to detect, but the two bodies are close enough for exchange to be possible. Scientists must compare predicted transport paths with actual chemical distributions. If the patterns match, the connection becomes stronger. If they do not, another explanation may be needed. This possible exchange does not mean Pluto is feeding Charon like a star feeds a planet. It is a much weaker process. Individual molecules can move through space. Some may freeze onto a surface. Others may be broken apart by radiation. The important point is that Pluto and Charon may not be chemically isolated from one another. They could share a long history of material moving between them. Their orbit makes the relationship permanent, but their chemistry may make it active. The system is also influenced by the Sun, even at such a great distance. Solar ultraviolet radiation continues to reach Pluto and Charon. The energy is weak compared with what Earth receives, but it is enough to drive chemical reactions. The solar wind carries charged particles outward. Cosmic rays arrive from beyond the solar system. These particles can penetrate surface ice and alter molecules. A world does not need to be close to the Sun to experience radiation. It only needs enough time. Time is one of the most important ingredients in the Pluto system. A single ultraviolet photon may change one molecule. A single energetic particle may affect a tiny patch of ice. Those individual events are insignificant, but billions of years of exposure can create chemistry across an entire surface. This is why frozen worlds can preserve evidence of ancient processes. Their low temperatures slow down many reactions. Their lack of thick atmospheres leaves surface material exposed. Their surfaces become long-term records of the space environment. The same idea applies to Pluto's haze. A small particle may not seem important, but a huge number of particles spread around the atmosphere can affect how sunlight and infrared radiation move. The haze can influence the temperature structure. It can also help transport carbon-based material toward the ground. Over time, that material may contribute to the appearance of Pluto's surface. A microscopic process becomes a planetary feature. This is a recurring pattern in planetary science. Large landscapes can be created by effects that begin at the scale of molecules. Pluto's atmosphere also changes with its orbit. When Pluto receives more sunlight, nitrogen ice can release gas and increase atmospheric pressure. When it receives less energy, nitrogen can condense and lower the pressure. Methane and carbon monoxide participate in related cycles. The timing is not simple because the surface is uneven and Pluto's rotation affects how sunlight reaches different regions. The atmosphere may respond with delays. A surface can remain warm after the sunlight changes. Frost can continue forming after a region enters a colder season. These delays make observations especially valuable. Scientists can compare thermal data from one period with atmospheric measurements from another. They can look for evidence that the surface and atmosphere are out of step. If the ground warms before the air responds, that reveals how quickly energy is transferred. If haze changes before surface frost moves, that shows the importance of upper atmosphere chemistry. Webb's data do not provide every answer, but they add another time point to a climate record that researchers are slowly building. The thermal behavior of Pluto is also connected to albedo, which is the amount of sunlight a surface reflects. Bright ice has a high albedo and reflects more energy. Dark material has a lower albedo and absorbs more. On Pluto, the difference between bright nitrogen ice and dark organic material can be significant. As one region warms or cools, the location of surface frost can change. That can alter the region's brightness. A change in brightness can then alter how much energy it absorbs. This creates a feedback loop. A bright surface may remain relatively cool because it reflects sunlight. A darker surface may absorb more energy and become warmer. Warmer areas can release more gas. That gas can travel and freeze in a different location. New frost can brighten another region. In this way, Pluto's surface and atmosphere can move energy and material across the planet. The process is slow, but it may help explain why Pluto has such varied terrain. The dwarf planet is not simply receiving sunlight, it is responding to it. The mid-infrared observations help separate temperature from reflected light. In visible wavelengths, a bright surface may appear bright because it reflects sunlight. In the mid-infrared, scientists can measure heat released by the surface and atmosphere. Comparing the two signals reveals how efficiently different regions absorb and emit energy. This is essential for climate modeling. Without thermal data, researchers would know what Pluto looks like, but not fully understand why it looks that way. Webb's position in space also matters. The telescope must remain cold to detect faint infrared signals. Its large sunshield blocks heat from the sun, Earth, and Moon. This design was mainly created for studying distant infrared sources, but it also helps when observing nearby cold bodies. Pluto's thermal emission is faint. The telescope must distinguish that weak signal from its own heat and from background radiation. The observation is a technical achievement as well as a planetary discovery. Some people may ask why a telescope designed to look at the early universe would spend time observing Pluto. The answer is that the same infrared technology is useful for many kinds of science. Webb can study the formation of galaxies, but it can also examine molecules in a nearby atmosphere. It can analyze warm dust around young stars and the cold surfaces of distant moons. Different targets require different observing strategies, yet they all benefit from sensitive infrared detectors. There's another reason Pluto is worth observing from far away. New Horizons could see the surface in close detail, but it could not remain in orbit around Pluto. Its encounter lasted a short time. Webb can return to the system and make follow-up observations. Repeated measurements can reveal change. A future observation may show a different thermal curve, a changing haze signal, or a new pattern in the atmosphere. Long-term observations are essential for understanding a world with seasons lasting decades. The first Webb observations do not represent the final word. Researchers still need better models of Pluto's haze. They need to understand the size and shape of particles. They need to determine how quickly the haze forms and settles. They must connect thermal emission with the distribution of nitrogen and methane ice. They also need to compare Pluto with other bodies in the Kuiper Belt. A single object can be unusual. A group of objects can reveal whether Pluto is typical or exceptional. Charon also deserves continued attention. Future observations may map carbon dioxide more precisely. They may show whether hydrogen peroxide is concentrated in particular regions. Scientists can compare the chemical signals with craters, canyons, and polar deposits identified by New Horizons. If a compound appears near certain types of terrain, it may reveal how that terrain formed. If the compounds are spread widely, radiation processing may be more important than local geology. The Pluto system may also help researchers understand icy bodies around other stars. We cannot send a spacecraft to those distant objects. We often see them only as points of light. But the physical processes operating on Pluto can help scientists interpret distant worlds. Haze, methane, surface ice, and infrared emission may appear in other planetary systems. By studying a nearby example in detail, researchers develop tools for understanding places they can never visit. The chemistry of Charon also connects to a larger question about the origins of planetary materials. Carbon dioxide and water ice were present in the outer solar system during its formation. Radiation changed some of those substances. Impacts exposed buried layers. Surface temperatures determined which materials remained stable. The final composition of Charon is therefore a combination of ancient ingredients and later processing. The moon preserves both the beginning and the long history of its environment. Pluto's situation is similar but more dynamic. Its surface contains old material, but its atmosphere continues to move. New haze forms. Existing particles descend. Nitrogen freezes and evaporates. Methane shifts from one region to another. The surface can preserve ancient clues while also changing in the present. This combination makes Pluto scientifically valuable. It is both an archive and an active laboratory. None of this means Pluto is warm, comfortable, or habitable. Its surface environment is extremely hostile to Earth-like life. Temperatures are far below the freezing point of water. Its atmosphere is too thin to breathe. Sunlight is weak. The surface is exposed to radiation. These facts remain unchanged. The discovery is not that Pluto resembles Earth. The discovery is that physical complexity can emerge in an environment radically different from Earth. That is a lesson planetary science keeps teaching. Earth is not the only place with weather. Titan has a methane cycle. Mars has dust storms and seasonal carbon dioxide frost. Venus has a thick atmosphere and powerful circulation. Europa has a hidden ocean beneath ice. Pluto has its own version of climate, built from nitrogen, methane, haze, and radiation. The details differ, but each world shows that a planet or moon can behave in unexpected ways. Pluto is also a reminder that classification does not determine complexity. Calling it a dwarf planet does not make it less interesting. Its size tells us something about its mass and gravity. It does not tell us whether its atmosphere is active or whether its surface holds chemical surprises. A small body can contain a complicated system. In fact, its small size may make some processes easier to observe because its atmosphere and surface respond strongly to limited energy. The phrase first time must also be used carefully. Webb was not the first instrument to observe Pluto. New Horizons was not the first telescope to detect it. Astronomers had studied Pluto's atmosphere and surface from Earth before Webb was launched. What Webb provided was a new infrared perspective. It extended the range of observations and allowed researchers to examine heat and molecular signatures with greater sensitivity. This is not a weakness in the story. It is the real strength of the discovery. Every telescope sees only part of the truth. A visible light camera may reveal terrain. An ultraviolet instrument may reveal upper atmosphere chemistry. A near-infrared spectrograph may detect surface ice. A mid-infrared instrument may measure thermal emission. Radar can reveal surface roughness. Radio observations can reveal gas and motion. When these different measurements are combined, a world becomes more understandable. Webb's contribution is powerful because it adds information that earlier observations could not provide. The faint light from Pluto and Charon traveled across the solar system before reaching the telescope. It may have been reflected sunlight, infrared heat, or radiation emitted by molecules. The signal was weak, but it carried physical information. Webb collected that signal with a mirror designed to detect distant and ancient sources. Scientists then removed background noise, separated the contributions of Pluto and Charon, and compared the results with models. The final discovery is built from many small steps. Those steps matter because dramatic images can hide uncertainty. A colorful picture may be processed to highlight invisible wavelengths. It may show a model rather than a direct view. A spectral feature may be weak and require careful statistical analysis. Scientists must test whether an apparent signal could come from the instrument or from another source. For Pluto and Charon, repeated observations and laboratory comparisons help establish which features are real. The most exciting conclusion is also the one that survives the most checking. Webb's observations of Charon passed through that process. The detection of carbon dioxide and hydrogen peroxide came from the pattern of light absorbed by the surface. Researchers compared the signal with known compounds and studied how the features changed across the moon. The result did not answer every question, but it provided strong evidence for the presence of those chemicals. It also opened new questions about how the molecules formed and where they are located. The same is true of Pluto's haze. Researchers can measure its effect on infrared radiation and use climate models to explore its cooling role. The models must account for sunlight, particle size, atmospheric pressure, surface temperature, and chemical reactions. If the model predicts a thermal pattern similar to Webb's observation, confidence increases. If the model fails, the haze chemistry may need to be revised. Science advances by making these comparisons. The most important change is the change in our mental image of Pluto. The old image was a distant dot discovered in 1930, a small object with a strange orbit. The later image was a frozen dwarf planet with a thin atmosphere. New Horizons added mountains, glaciers, and possible geological activity. Webb now adds a thermal and chemical layer. Each stage has made Pluto less simple. The object has not become larger, but our understanding of it has expanded. Pluto's haze may be cooling its atmosphere while its surface continues to exchange ice and gas. Charon's surface may preserve carbon dioxide, while radiation creates hydrogen peroxide from water ice. Material may move between the two bodies. The sun may provide only weak energy, but that energy still drives chemistry. None of these facts stand alone. Together, they create a system that changes slowly but continuously. This is why the observation matters beyond a single telescope. It shows how much can remain hidden even after a spacecraft has visited a world. New Horizons gave scientists a close-up view, but Webb revealed processes that require thermal measurements and broader spectral coverage. The two missions complement each other. One showed where the mountains and plains were. The other helps explain how the environment around them works. A future mission to Pluto could answer even more questions. An orbiter could watch the atmosphere through multiple seasons. It could map the distribution of surface ice at high resolution. It could measure haze particles directly. It could study Charon and perhaps other moons in the system. Such a mission would take years to reach Pluto, but the scientific return could be enormous. Until then, Webb provides a way to continue studying the system from a great distance. The outer solar system is often described as dark, cold, and empty. That description is understandable, but incomplete. The region is dark compared with Earth. It is cold compared with every familiar environment on our planet. Yet, it is not empty. It contains worlds with atmospheres, moving ice, radiation chemistry, and complicated histories. Pluto and Charon show that the edge of the solar system is not a dead boundary. It is a place where slow processes continue. The most unsettling fact is that these processes are easy to underestimate. A thin layer of haze can affect atmospheric temperature. A small amount of carbon dioxide can reveal buried or altered surface material. Radiation acting on ice can create a new molecule. Weak sunlight can move nitrogen across a planet. Each process sounds minor when described alone. Together, they can shape the appearance and climate of an entire world. Webb's view of Pluto therefore changes the question we should be asking. The question is not whether Pluto should be active. It is how such a cold body can remain active for billions of years. The answer appears to involve a balance between weak sunlight, volatile ice, atmospheric chemistry, radiation, and time. The balance is fragile, but it is real. Pluto does not need Earth-like conditions to have a climate. It also changes the way we understand moons. Charon is not merely a companion visible beside Pluto. Its surface has its own chemistry and history. It may preserve compounds formed during the solar system's early years. It may also record the effects of radiation and impacts. Studying Charon gives scientists a second example in the same system. Comparing the two worlds shows how different outcomes can emerge from related beginnings. The new findings do not prove that Pluto and Charon have an atmosphere like Earth. They do not prove that liquid water exists on the surface. They do not show that the system contains life. Scientific honesty requires saying exactly what the observations support. The observations support a dynamic haze, thermal variation, changing surface processes, and chemical compounds on Charon. Those facts are already remarkable. They do not need to be exaggerated. The dramatic part is hidden in the details. A faint infrared signal can reveal a cooling layer. An absorption line can reveal carbon dioxide. A second spectral feature can reveal hydrogen peroxide. A change in thermal emission can reveal that two nearby worlds respond differently to sunlight. The discoveries are not loud. They arrive as data, but once the data are interpreted, the simple picture of Pluto becomes impossible to maintain. The word impossible should also be used carefully. Pluto's behavior does not violate physics. In fact, the observations are valuable because they show physics working in an extreme environment. Molecules absorb energy. Particles radiate heat. Ice changes phase. Radiation alters chemical bonds. Gravity holds the system together. These are familiar laws. What is surprising is the way they combine at the edge of the solar system. When Webb pointed toward Pluto, it was not searching for a miracle. It was measuring a faint world with instruments designed to detect infrared information. The telescope collected light. Scientists separated the signals. Models explained how the light could have been produced. The result was a picture of Pluto as a working climate system and Charon as a chemically altered moon. The discovery is powerful because it came from ordinary science applied with extraordinary sensitivity. Pluto's atmosphere may continue changing as it moves along its long orbit. Some regions may lose frost, while others gain it. The haze may grow or thin. Thermal emission may change as the surface responds to seasonal sunlight. Charon may continue to preserve radiation products on its ice. Future observations can test these predictions. Each new measurement will show whether the current models are correct or whether another piece of the puzzle remains hidden. The next surprise may come from Pluto itself, from Charon, or from another distant body in the Kuiper Belt. Webb may find that Pluto is unusual. It may find that many icy worlds have similar haze chemistry. It may reveal that carbon dioxide and radiation products are common on large moons. Either result would be important. A rare Pluto would teach us about exceptional conditions. A common Pluto would reveal a broader pattern across the outer solar system.